Okay, suppose let's talk about this topic: new functions from old functions. So if we start with a function f of x, question is what does f of x plus c look like? For example, suppose f is x squared. What does f of x plus 2 or x squared plus 2 look like? So if we have that one, so that's y equals x squared supposedly. So what about this function? So then when x is 0, before when x was 0, we got 0 squared or 0, so we had the origin. Now when x is 0, we get 2. And you can see that 0 is the lowest point of this graph. In other words, as soon as you put anything other than 0 in, it gets bigger. And the same thing here, as soon as you put anything other than 0 in, you're going to get some contribution here. So I think we can see that, or maybe you can see that this looks like that. In other words, it's this one, but shifted up by 2. And if it hadn't been f of x plus 2, but it had been f of x plus 5, then it would just be shifted up by 5 instead of by 2. So then it would be like this. And if it had been f of x minus 2, then it would have been shifted down by 2, so it would have been here. And this isn't just true for the function x squared, but for any function f, if you add 2 to it, if you add 2 to it, it's going to shift the whole thing up. So if you started with a function that looked like, say, that, now I'm never going to be able to repeat that drawing, but, and if you add, or let's say if you add 1 to it, so if this is f, and you consider what would f of x plus 1 look like, I'll never be able to do that again, but I guess it would look like, would kind of cross up higher and then go up higher. So this, if this was, say, a, where it crossed, then this would be a plus 1. So that's the relationship. So it would be up here. Like that, with this distance being 1, and this distance being 1. Okay, so now what if we start with f of x, and we wonder what's the relationship between the graph of this compared to f. Before we had a on the outside, but now we're changing the so-called argument, subtracting a or adding a. For example, suppose that f of x equals x squared again, and suppose we now ask what is f of x minus 2 inside. So what does that look like? So of course we know that that looks like x minus 2 squared, because whatever we put in for x, we're supposed to square it. We're putting in x minus 2, so we have to square that. But how can we imagine the difference in the two graphs? So we start out with x squared, like that. And now we're wondering about this. So we can ask, well, where is the lowest point for this? Obviously, the lowest point is when x, so let's say the lowest point is when x equals 0. So let's just say the lowest point is when what's inside is 0, because that's going to be, then this thing is, then when you square it, it's also going to be 0. So now we can ask, well, where's the lowest point of this then? It's still going to be where this thing is 0. When this thing is 0, then when you square it, you're going to get 0. And if this thing is not 0, then when you square it, you're going to get something greater than 0. So when is this whole thing going to be lowest? When this thing is 0. But when is, so we can say, so when is x minus 2 equal to 0? Well, that's when what? When x equals 2. So that's when this is going to be lowest. So in other words, when x is 2, this is going to be at its lowest point. And everywhere else, like suppose when x is 3, that's going to be 3 minus 2, that's going to be 1. That's going to be the same thing that this was when x was 1. In other words, when x was 1 here, it's going to be the same thing as when x is 3 here, because when x is 3, then you're putting in 1 in here, or you're squaring 1, and so you're getting the same thing that you would when you put 1 in to here, because that's you're also squaring 1. So in other words, when this is 0, when x is 0, we get the lowest point. When here, when x is 2, we get the lowest point, and then it behaves exactly like this to the right and the left. So in other words, it looks like this and like that. Well, I didn't draw them. These are supposed to be sort of the same. But so basically what happened was we'll shift this parabola over 2 units when we do this. So it looks like we're going to shift it to the left 2 units, but no, we end up shifting it to the right by 2 units. And that's not just true for f of x equals x squared, but for any function. For example, if f of x was equal to the sine of x, we could say, what about the sine of x minus 2, or if you wanted to be sort of more in the realm of trig functions, you might say, what's x minus pi? But whatever. Anyway, let's just do this one. So if the sine function normally, where does it, when the sine of 0 is what? Is 1. No, sorry, the sine of 0 is 0, right? So it looks something like this, right? So what is this going to look like? It's going to be the same shape as the sine function, but it's not going to start here. It's going to start at 2. It's going to start because it shifts over, so it's going to look like that. Okay, so no matter what function we are dealing with, we start with the sine function and we subtract 2 from it, then the whole thing moves over to the right by 2. And on the other hand, suppose we did, let's go back to y equals x squared, or f of x equals x squared. And then we ask, what about f of x plus 2? What's that going to do? We already saw that minus 2 moved it to the right by 2. And thinking of it in the same way, if we start with this function like that, y equals x squared, then we can say, well, when is this going to be at its lowest point? In other words, when is the argument to this going to be equal to 0? Because that's when this is x plus 2 squared. And when this was, this is at its lowest point when the argument is 0. And this is the squaring function, but we've just changed the argument. So we still want the argument to be 0. So when is that going to happen? I mean, if we want to know when it's going to be lowest, we want the argument to be 0. And when is that going to happen? When x plus 2 equals 0, that means what? X equals minus 2. So this is going to be lowest point there. So in other words, it's going to be shifted. I can't do that, but it's going to be shifted. So this is going to be shifted over by 2, to the left, though, this time. So when we add 2 to the argument, we shift to the left. When we subtract 2, we shift to the right. And we also saw just before that if you take f of x plus a, you shift up. And of course, if you take f of when a is positive, and if you take f of x minus a when a is positive, then you shift down. So now we know how to shift to the right, to the left, up, and down. Okay, now we can ask, what if we start with y equals f of x, and then we consider f of x with some constant times f of x. So what does that do? Again, let's just take the same example. Suppose f of x equals x squared. We want to consider something like, what's the relationship of this graph to 3x squared? So again, we get this. But now, whereas when x was 2, we got 4. Now when x is 2, now when x is 2, we get 4 times 3, so it's higher. So 2 is going to be way up here at 12. But at 0, they're still going to be the same. So when x is 0, this is 0. And when x is 0, this is also 0. So even though it grows more quickly by a factor of 3, it reaches 0 here at the same place. So it grows, so it's more steep. So it's going to be something like this. Still what we call a parabola, but they say it's stretched. By a factor of 3. Okay, now what if we consider something like this? F of x compared to f of k x. So what does that do? We already considered adding something to the argument. What if we multiply? So for example, again, suppose we have f of x equals x squared, and we think about what is this? F of 3x, like that. What is that? What's the relationship of the graph of this to this? So 3x squared, 3x like that would give us 9x squared. So we know what that's going to look like. That's going to be, so if this was the original, then the new one is going to go up much more quickly because it's 9x squared. Okay, let's think about the same kind of thing when we're talking about the sine of x. So the sine of x versus the sine of, let's say, 2x. So what is this going to do? So again, the sine of x is starts out at 0, and when does it reach 0 again? Well, let's see if I can do this. So when does it reach this? When does it repeat itself? At 2 pi, and it reaches 0 at pi. Forget this mark. And this is pi over 2, right? That's when it reaches its highest point. So that's the sine. Now what about the sine of 2x? So what happens there? So we already considered what happens to the sine of x plus 2 or x minus 2. But this is different. Sine of 2x. So how long does it take for this to go through what we call one full period? So it takes 2 pi. X goes from 0 to 2 pi. This thing goes all through the whole cycle, and then it repeats itself again, right? So how about this, though? How long will it take for this to go through a full cycle? Well, the argument still has to go through 2 pi, but x doesn't need to go through 2 pi because we're multiplying x by 2. So if x goes from 0 to pi, then 2x will go from 0 to 2 pi, and that's what sine is looking at. So when x goes from 0 to pi, the sine should go through its full cycle. So if I can draw it, which I can't, but there it is. Okay, so, and it's supposed to be the same height as this, which it doesn't look like. This is supposed to go from 1 to minus 1, and this is also supposed to go from 1 to minus 1. So the scale changed, I guess, because of my handwriting. So anyway, from 0 to pi, it goes through the full cycle. Okay, so what happens then? We can say that when we put 2 in, this kind of gets compressed in the horizontal direction, right? So whereas it needed to, in order to go through the full cycle, it needed to go from 0 to 2 pi. Now it only, to go through the full cycle, has to go from 0 to pi. So it gets compressed in the horizontal direction by a factor of 2.